If there's time at the end of class today, I'm going to talk a little bit about the conference I was at and just how you can use simple code to actually build up some intuition and make some reasonable conjectures. And so we were trying to prove a deep theorem. We were having trouble, so I suggest, well, I always yell at my students to write code and do some simulations. Maybe we should do that as well. And amazingly, the code is suggesting what the answer is. We don't know how to prove it yet, but it is extremely powerful. All right, so what I want to do now is let's do it this way. Coin tosses and the central limit theorem. If there's time at the end of today, I'll pass out pennies and we can actually talk and simulate doing this. What I want to do is I want to prove the central limit theorem in a very simple case, the case of fair coins. So we get to choose what do we want a head to be and what do we want a tail to be. Why don't we use heads and tails as the outcome of our random variables? So why don't we use heads and tails?
0 and 1's easier, just in terms of counting.
More than just easier. You're close.
Numerical.
Numerical. We want to be able to combine things. We can't combine 3 heads and a tail. So when we're tossing coins, we have a choice. We could make heads 1 and tails 0, and there's another choice we could do. What's the other choice?
Negative 1/2 and 1/2.
We could do negative 1/2 and 1/2, or we could do negative 1 and 1. So we have 3 choices. I'm going to rule out negative 1/2 and 1/2 because we're going to have enough algebra going through this that I do not want to have fractions. So do we prefer 0, 1, or do we prefer negative 1, 1? What do you think? Negative 1, 1. Why negative 1, 1? It has mean 0. I'm sorry?
Isn't the variance also 1? It has to be like
The variance will also be 1. And in fact, you almost have a symmetry argument because they're both equally spaced from the mean, and that spacing is 1. So we're going to choose each xi to be 1 with probability 1/2, negative 1 with probability 1/2. So the expected value of xi is 0. The variance of xi, if you just do the calculation, is 1. And if you want to do that directly, you could calculate the expected value of x squared. Well, what's x squared? 1. Doesn't matter what point you choose, x squared is always 1. So the expected value of x squared is 1. The expected value of x squared is 0. So this also means the standard deviation is 1. How many coins should we toss? No. Close, but no. No. We got to get ready for homecoming. We got to be done well before then. N is close. 2n. Why 2n over n?
So you can look at the excess of heads to tails.
Basically, it's going to normalize things a little bit nicely. If you toss an odd number of coins, you know you're going to either be at plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 7. If you toss an even number of coins, you're going to be at 0, plus or minus 2, plus or minus 4, plus or minus 6. You could, of course, do the analysis with generic n, but I think it's a little bit easier. And so we'll toss 2n independent coins, and we'll let x be x1 plus x2n. So what's the expected value of x? Zero. And then the variance of x, well, because they're all independent, the variance of the sum is the sum of the variances. So the variance is going to be 2n times the variance of each one, which is 1. And so what that means is the standard deviation of x is square root of 2n. What matters here is not so much the square root of 2, but the square root of n. It's telling us that if we were to toss these coins this many times, we expect to be at the origin, and our fluctuations we expect to be on the scale of square root of n. One of the best quotes in any of my undergraduate textbooks was from my statistical mechanics book. And the way a lot of people explain this is they talk about a drunk staggering home late at night from a lamppost. And at each moment, the drunk tosses a coin, and with probability 1/2 staggers to the left, and with probability 1/2 staggers to the right. And the question is, where is the drunk as time passes? You can then make things a little bit more interesting, and the drunk could stagger in 2 dimensions. The drunk could go left and right, forward and backwards. You can then have the drunk staggering in 3 dimensions as well. Well, most of our drunks can't really start flying or whatnot like that. So maybe it's Superman now, or Supergirl, the new TV show my kids like. Something like that where you have 3 dimensions. And you can start asking the question, what is the probability the drunk returns home? And something strange happens. It's 100% in dimensions 1 and 2, but not in dimension 3. And one of my professors in college said this is why we live in 3-dimensional space. It's the smallest integral dimension where life is interesting for drunks. You can't prove or disprove that, but. So there's a lot of stuff in the literature. It's called the random walk problem. They often use this to model incorrectly the stock market. You expect fluctuations to be on the order of square root of n. And so my statistical mechanics book, goes through and analyzes this and then says, now the main point of physics is not to help drunks staggering home late at night from lampposts. I like that this is not the main point, but that it is a subsidiary concern of physicists. Right? We expect to be square root of n away. Would you be surprised if we were 4 times square root of n away? How would you try to figure out the likelihood of being 4 times the square root of n away? Yes. We could use Chebyshev. And so if we think about the standard deviation is on the order of square root of 2n, if we were 4 root n, how many standard deviations would that be? It would be 2 root 2 standard deviations. Well, the probability of being 2 root 2 standard deviations away would be 1 over the square of that. Well, the square of 2 root 2 is 8. So if we just use Chebyshev, the probability of being as large as 4 root n, or higher, is 1/8. So if we just use Chebyshev, we can't rule out the possibility of being that far away. The central limit theorem, however, tells us that this is converging to being a normal with mean 0 and variance square root of 2n. And then if you do the calculation using a normal, the probability that you're so far away as to being 2 root 2 standard deviations away, it's much less than 1/8. Much, much less. So Chebyshev, if we try to be very close to the standard deviation, is not going to give us a good bound. But if we start going a little bit above the standard deviation, if we go something that's growing with n, then Chebyshev will be pretty good. So for example, what is the probability that the absolute value of x is greater than log n times the square root of 2n? So according to Chebyshev, what's this probability? So what would that probability be according to Chebyshev?
Less than or equal to 1 over log n squared.
Good. So if n is huge, it's effectively 0 chance of being more than log n standard deviations away. We could have an even stronger question. We could say, what's the probability that x is greater than, say, n to the delta square root of 2n? Well, that would be less than or equal to 1 over n to the 2 delta. And we'll take delta to be some exponent less than 1/2. So we can bound very nicely the probability that we are significantly above the standard deviation away, as long as it's growing. So again, think of n as enormous. Think of n as a trillion, a quadrillion. This is going to be an extremely small probability. If I can understand 99.999999999% of the mass, I basically understand the whole system. What this is telling us is, depending on how good of a bound we want, we might want to allow ourselves to go more standard deviations away. So the advantage here is that my sums x don't change that much. My sums x are all about size square root of 2n. Over here, if delta is 1/4, my sums could be as large as n to the 3/4, and there could be some large fluctuations. So we'll see now why we care about something like this. What is the probability that x equals 2k. And why am I going to write it as 2k? So yes.
Because we're tossing an even number.
Yeah, we're tossing an even number of coins. The probability that I'm at 2k plus 1, that I'm at an odd value, is 0. If I toss an even number of coins and every head is a plus 1 and every tail is a minus 1, I know all the evens are accessible and none of the odds are. And that's going to come back and bite us later today. We're going to have to fix that. But let's just analyze the evens now. How could we end up being 2k units from the origin? What would that mean? We get 2k more heads than tails. So how many heads do we have? They've got to differ by 2k, and what do they have to add up to? 2n. So you want to write it as, it's n plus something, n minus something. They've got to differ by 2k. So with a little bit of inspection, you get it's n plus k and n minus k. That's how we would end up being 2k units away. Now we have to look at all the sequences of coin tosses where we end up having n plus k heads and n minus k tails. What's the probability when we toss a fair coin 2n times, or equivalently when we toss 2n fair coins independently, that we have n plus k heads and n minus k tails? Okay, so this would be 2n, choose n plus k, a half to the 2n. So if we want to be really pedantic, it would be 1/2 to the n plus k, and then 1/2 to the n minus k. And you can begin to see now why we're using a fair coin. If we were using a coin that was not fair, I would have two different numbers in here, and I would have that complication going on at the same time. Well, because these are the same, this simplifies very nicely, and it's 2n factorial over n plus k factorial n minus k factorial 1 over 2 to the 2n. And that's because these just combine. What's nice is this part here now has no dependence on k. All the dependence on k is here. So all we have to do now is see that as n goes to infinity, this is converging to being the density of a normal. Hopefully you can begin to see now why we are using Chebyshev. How would you like to approximate this? What could we use to approximate this? We could use Stirling. What must be true if we're going to use Stirling's formula? So what is Stirling's formula used for? You got to know this. What do we use Stirling for? Approximating factorials. So if I wanted to approximate 4 factorial is approximately 4 to the 4th e to the minus 4 square root of 2 pi times 4. Can I do that? How comfortable are we with this as an approximation for 4 factorial? Not that.
N has to be like big, right?
N has to be big. So with the 2n going to infinity, I'm not worried about using Stirling upstairs. Downstairs, if k is really close to n or really close to 0, then one of these expressions might be small. What if k is equal to n minus square root of n? Then this could be a much different power of n than what's upstairs. By confining k to be much smaller than n, we know that 2n, n plus k, and n minus k are all going to be approximately the same, and that it'll be very reasonable to use Stirling's formula to estimate. This is why we're using Chebyshev. Chebyshev localizes the values of k we need to consider. So we're not considering the case where we toss the fair coin and 75% of the coins come up heads. Well, if n is large, the probability of 75% of the coins coming up heads, this is negligible. If there is time, I will send an email. So I know somebody was making some jokes about the Patriots earlier today. There was an article in one of the sports websites that the Patriots seem to have powers over the coin toss and are winning the coin toss more often than the laws of probability would dictate. And yes, there's some questions as to whether or not Bill Belichick has the powers of Magneto to affect how the coin is being tossed as the officials throw it in the air. And then the question is whether or not the Patriots are cheating on the coin tosses. So I will send some stuff on that. We can assume when we're tossing billions of times, we do not have to worry about 75% of the time being heads. We don't even have to worry about 2n to the 3/4 of the time being heads. Basically, k is going to be very close to 0. K is going to be approximately some multiple of square root of n. Once we get to k is as large as log n times square root of 2n, the probability that k is larger than that is so small that we can essentially ignore it. And so you can either do it with a little bit of a log savings or you can do it with a power savings. Okay, so now we want to use Stirling. And so I'm going to just remind us what Stirling is. So Stirling is that m factorial is about m to the m e to the minus m square root of 2 pi m. I'm not going to go through the rest of the details as to what the error terms are. You can make this precise. You can put in careful estimates and make all these arguments rigorous. I want to just give you a rough sense right now of why Stirling is true. If you want, I'll give links to the 2 videos in complex analysis where we actually proved Stirling's formula for the most part today and on Monday. So now we want to just estimate all these various things. There's a lot of ways to do the estimation. Is there anything that you should have in your mind as we're going about this? Anything you should be thinking about?
Simplifying it?
Okay, how?
Reducing terms, like canceling.
So one thing is when we start putting this in, we're going to get an enormous amount of simplifications. But there should be something else lurking in the back of your mind as you do the algebra. This is why I don't want to just run through the proofs. I want to really go through this slowly and give you a sense of how you attack stuff like this. You should immediately be thinking something as soon as you see this expression. What should you be thinking?
Dependence on k.
There is dependence on k. What is 2? Yes?
We can cancel stuff out.
We can cancel stuff out, but there's a certain process going on here. And you should be thinking something every time you see this process. What does 2n factorial mean? So when you see all this multiplication, what should you be thinking? You should immediately be thinking logs. Think logs. There's a good chance logs are going to come into play in the analysis because we have products. So let's start doing the simplification. So 2n factorial becomes 2n to the 2n e to the negative 2n square root of 2 pi times 2n. Downstairs, we have the n plus k and n minus k. If you want, all I'm doing is for the most part in the book. If you want to just denote like the key ideas, that's fine. The algebra is in the book. So we have n plus k. So we have n plus k to the n plus k e to the negative n plus k square root of 2 pi n plus k. Then we'll have n minus k to the n minus k e to the negative n minus k square root of 2 pi n minus k. And now we also have the 2 to the negative 2n from this piece over here. All right, there's going to be a lot of cancellation. We have a 2 to the 2n, a 2 to the negative 2n. The 2's cancel. We have an n to the n. We have an n plus k to the n plus k. We have an n minus k to the n minus k. I can pull this n downstairs into each of those. I pull n plus k of n's into here, and I'll get n plus k over n. And I pull n minus k n's into here, and I'll get n minus k over n. Okay? And so when I do that, these will become 1 plus k over n. This will become 1 minus k over n. I have an e to the negative 2n, and when you combine these, I have an e to the negative 2n. Those will cancel. Square root of 2 pi, square root of 2 pi, square root of 2 pi. A square root of 2 pi survives down below. Because we know k is not that large relative to n, the square root of 2n over n plus k, well, square root of n is basically the same size as square root of n plus k. And we'll have a square root of n over square root of n minus k, which is about a square root of n, because k really doesn't differ from 0 by that much. So when you do the algebraic simplifications, this is all down, so you get 1 plus k over n to the n minus k, 1 minus k over n, I'm sorry, this is to the n plus k to the n minus k. The 2 pi, this one cancels with this one survives, this n cancels with this n. We have a square root of 2 that survives up here, we have an n down here. It should be a square root of 2 over 2 pi n when the dust settles. Yes?
The n minus k in the far right of the denominator, that is under the root, right?
Yes, it's under the root. Yes, thank you. And if you want to multiply these two together, this will look like n squared minus k squared. We have an n above, so n over n squared is about 1 over n. When k is very, very large, n is so much larger than that that I can just do this approximation, and it's going to be fine. Okay. Now, n is extremely large. When n is extremely large, what does 1 plus k over n look like if I raise that to the nth power? What do you think 1 plus k over n to the n looks like if n is huge? Not 1, close.
1 plus n plus k times k over n.
Nope.
Or using
Not close to e, but not quite e.
Are you saying what does 1 plus k over n look like?
Yeah, if I raise it to the nth power.
1.
So e to the u is the limit as n goes to infinity of 1 plus u over n to the n. So if I let n get very, very large, what do you think this factor looks like? E to the k. Have you ever seen the crossbones in mathematics? It means be careful, you may have done something dangerous. Okay, I'm putting this as a warning. I've given this lecture several times. I know exactly what's about to come from this. So we would approximate this as e to the k. What would we approximate this piece? E to the negative k. And then we have the 2 actually cancels, and we'd have the square root of 1 over pi n. What distribution is this converging to? What kind of distribution is this looking like? As you vary k, uniform. This is looking like the uniform distribution. We must have done something wrong. We're supposed to be getting a normal, we're getting a uniform. The problem is in this analysis here. K does have n dependence. In this, 1 plus u over n to the n, u is a fixed number. K is growing with n. That's a problem. We could try to fix this and say, well, look, we could write here, I'll write this on the side over here. We could write it as 1 plus 1 over n over k, and raise this to the n over k, and then raise that to the kth power. And if we do that, what does this piece over here look like? What would this piece look like? E. And then that would still give us e to the k. The danger with this is k is growing, and we have to be very careful about our approximation. If we're off by just a little bit, we're magnifying this so many times because k is very large that our errors could be propagating. We're also dropping the fact that we have a plus k over here. And if k is on the order of square root of n, well, k over n is of size square root of n. Ooh, k is also of size square root of n.
Sorry, should it be 1?
Oh, sorry. You're right. It should be 1 over all this. Thank you. It should be 1 over. Because these were in the denominator. I'm sorry.
Now it makes almost less sense.
Well, we had an n plus k down here. I move an n downstairs. And so if you want, multiply by 1 over n to the 2n. We move over here 1 over n to the n plus k, and over here 1 over n to the n minus k. And now I can move this into the denominator.
I think it also would have worked if the plus and minus were switched. I don't know. Because n over n plus k is 1 minus k over n. And n plus k over n is 1 plus k over n.
Right, that's what these are over here. So that's just taking the n to the n upstairs and moving it downstairs.
Okay.
The difficulty is you've got to be very careful with your approximations. And if we just try to trivially approximate these with e to the k or something like this, we're not being careful enough. And small errors are being magnified. If you have a small error and you do it 5 or 6 times, it's not going to be a big deal. But if you have a small error and you do it a number of times that's going off to infinity, a small error that's being magnified that many times can now become sizable. So here, if you want, I'll do that step a little bit slower. We have n to the 2n over n plus k, n minus k. So I multiply by 1 over n to the 2n, 1 over n to the 2n. The top now just becomes 1. And then down below, these were n plus k, this is n minus k. We have 2n factors downstairs. I have 2n factors of n. I bring n plus k of them into the first piece. And so I'll have n plus k over n to the n plus k. And then the second one I'll have n minus k over n to the n minus k. So when we tried to do it too quickly, we made a mistake. So what we have is we have 1 plus k over n to the negative n plus k, 1 minus k over n to the negative n minus k, and then square root of the 2's cancel 1 over pi times n. So we want to figure out how to analyze this. And if we just try to replace this with the exponential, we made a mistake. And the reason we made a mistake is these exponents are so large that if we make a small mistake in the approximation, when we then do all the multiplication out, that small mistake propagates enormously. Any ideas how we could try to approximate this better? What could we try to do a better job of approximating this? What should we try?
We could split up the 1 to the power of the n and put them together.
We could try to do that together, but the problem is we've still got a lot of things with k's and n's that are growing, and they're growing together. And it's dangerous when you have things growing together. We need some way to deal with this huge product. Logs, right? There's a reason why I'm saying, think logs over here. There's a reason why I wrote that down. Yes?
Should that be square root of pi n? Since it was in the denominator before?
Did I drop it? Was it supposed to be in the denominator? No, this part was not in the denominator. This part was we had a square root of 2 pi up here, and we had 2 square roots of 2 pi's down below. So a square root of pi survives in the denominator. We have 1 n upstairs, 2 n downstairs, so an n survives down there. So we want to think logarithms. So when we have something like this, when you have a massively complicated expression like this, a really good way to do this is to do logarithms. So now let's look at the log of the probability that x equals 2k. So now when we start doing logarithms, we take the log of the products. We get negative n plus k, I'm sorry, yes, negative n plus k, the log of 1 plus k over n. Now we have minus n minus k, the log of 1 minus k over n. And then the last part is the log of the square root of 1 plus pi over n. Do I really need to worry about understanding the log of the square root of 1? No, that part's fixed. It's this part over here, this is the meat. Now the whole point of calculus is you take a complicated function and you replace it with a simpler function that's easier to understand. If you look at what we have now, this is exact up to small errors from Stirling, but you can show that the errors from Stirling are much lower order than what we have. We want to understand this nightmarish expression. The reason things are so bad is this number here is greater than 1. So when we raise this to the power n plus k, it becomes a huge number. This number is a little bit less than 1. When we raise this to this power, it becomes a very small number. And now we're multiplying a very large number by a very small number. And this is fraught with danger. There's a really good chance of making a mistake here. We want to do a good job of understanding the different relative sizes. Well, now we can expand. So what should we use? And we've seen it already this semester. It's almost, it's very much related to the harmonic. Where are you getting that from?
We did the marriage problem?
It's not quite the marriage problem. Taylor series. Taylor series for which function? And that's going to have the harmonic numbers coming out. The log of 1 minus u, or we'll do 1 plus u, is going to be u minus u squared over 2 plus u cubed over 3 minus u to the 4th over 4 plus dot, 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 dot. We saw this with the birthday problem. When we were trying to do the product of all that, it was kind of like a factorial. And the way we understood this, and we saw how accurate this was with the birthday problem, when u is small, just keeping the first term is pretty good. We might keep the first 2 terms to be safe, and then the third term is going to be negligible. So again, what I want to do is I want to give you a real sense of how you do the analysis. On the exam, I will not give you a problem of this level of complexity. We will need to do something of this order when we prove the central limit theorem. So interestingly, the arguments we're doing here are very similar to the arguments that we're going to do when we prove the central limit theorem. This is good. Whenever you have a very bad calculation, you want to see it multiple times. So this is going to be our first pass on this analysis. Let's try to figure out how many terms we need to keep. This is small. So you might say we only need to keep 1 term because it's small. Why might we need to keep more than 1 term, even though the log of 1 plus k over n is really small? Why might we need to keep multiple terms? We're multiplying it by something really big. So because we're multiplying it by really big, we can't just stop after 1 term. Well, let's think of how big is it. It's going to be of size n. This is going to be of size k over n. So if we just look at the first term, when we multiply out, we'll get n times k over n. We'll get something of size k. The next term will be k squared n over n squared. So we'll get k squared over n. We expect k is of size square root of n, maybe a little bit larger. So k squared over n is going to be roughly of size 1. When we get to the next term, we'll have k cubed over n squared. K cubed is only going to be a little bit more than n to the 1.5. N to the 1.5 over n squared, this is going to be decaying like 1 over square root of n. Maybe it'll be like log squared over square root of n, but it'll be much, much smaller. So by the time we get to the cubic term, it's going to be a negligible error. And this is going to give us a more accurate expansion. If we just try truncating after here, we're still missing a sizable contribution. All right, so now we have to do a lot more algebra. All right, so now we have n plus k And now we've got the first term is coming from u, so we're going to get k over n minus k squared over 2n squared plus, I'm going to write an error, e for an error, of size k cubed over n cubed. So if I look at what's going on from all these other points, if I go further down, it's an alternating sum. Wonderful. And even if it wasn't alternating, I'm getting decay from the denominators, and each one of them, it's bounded by a geometric series. I'm getting higher and higher powers of k over n. As I go further and further down, it's no problem. The error is going to be of size k cubed over n cubed. Let's look at the next piece. Now we're going to get a minus n minus k, and now we'll have u is now going to be negative k over n. So we'll get a negative k over n minus k squared over n squared plus some, that's horrible, plus, I'm having trouble writing my errors. I'm making errors with my errors. Error of k cubed over n cubed. And I'm only working with the first two terms. I'm not working with the constant term. I understand a constant term. Okay? These errors don't have to be the same. I could just take the large of the two if I wanted to. Now let's look and see what happens as I multiply. I have the n times k over n. I have a negative n times a negative k over n. So what's going to happen with those terms? Oh, there's a minus sign from here, sorry. There's a minus sign here. So we have a minus n times k over n, and we have a minus n times minus k over n. So what happens when the n hits these terms? What do we get? They cancel. That's why it's so important to be doing the analysis like this very carefully, is we're having these things canceling off in pairs. Now we have the minus n hits this. What does this remind you from algebra class all those years ago? FOIL. We're just doing it very slowly. So we'll have a minus n times a minus k squared over 2n. So that piece will give us minus times minus is a plus, right? Yes? Minus times minus is a plus. Okay, just making sure. So we get k squared over 2n squared from this. And from this one over here, we have a minus and a minus is a plus. And now that makes it a minus. Oh, no, sorry. A minus n here, hitting the minus this becomes a plus k squared over n squared. So do we agree that those two terms give us a 2k squared over 2n squared? Now when we look at the next term, we're going to get an error of size k cubed over n squared. Yes?
Should there be a 2n squared in a second?
Yes, thank you. There should be 2n squared. Thank you. I did keep that over here when I wrote it, but yes. So now when I move over here, we're going to get an error of size k cubed over n squared. And now you can begin to see why we used that Chebyshev before. If k gets too large relative to n squared, we're in trouble. How large could we take k? Well, it looks like k could be, if k is a little bit less than n to the 2/3, we should be okay. So over there we were writing delta up to 1/2. Going delta all the way up to 1/2 is probably too much. But if we keep delta to maybe 1/4, or if we do something even stronger, letting k only go up to like log n times square root of n, we'll definitely be fine. And this will be negligible. All right, now we've got to do the rest of the formula. Now we've got to do the negative k times this. So negative k times k over n is negative k squared over n. And then over here, negative and a negative is a positive, and a negative, so we get a negative k squared over n. So we get a minus 2k squared over n. Everybody agree with that for the next term? All right, now marching down the line, now we have the k hits that. What size is that going to be? when the k hits the k squared over 2n squared, what size is that going to be? K cubed over n squared. That's already the same size as our error. So when we continue to do the FOIL, this piece just comes straight into this error term. And this piece just goes straight into the error term. If we then go even further and do the next pieces, those go straight into the error term. Which makes sense. K is smaller than n. So as we do the multiplication with n, more terms will contribute when we multiply by n than we multiply by k, because the n is larger. We shouldn't have to go as far when we're dealing with k. All right, so we have 2k squared over 2n squared minus 2k squared over n. What does that equal? I'm getting k squared over 2n. Oh, sorry, this should be an n squared. Or, wait, did I drop things? The other one should be an n. I get k squared over 2n. I'm sorry?
Should it be negative k squared over n?
Oh, yes, I'm sorry, I dropped the negative sign as well, sorry. I want to make sure I have the right factor of 2. You know, this is just k squared over n. This is 2k squared over n. Oh, so maybe is it just k squared over n? Just k squared over n. Okay. So do we agree that this is just negative k squared over n? And this was the log of the probability. So that means the probability we would have to exponentiate. Okay, so there's still unfortunately danger we've made a small algebraic mistake, but let's hope not. All right, so what we'll do is we'll come back. And so now if we continue, we get the probability that x equals 2k. So we need to exponentiate. So we get e to the negative k squared over n. And now we have a 1 over the square root of pi n. What does this look like? Looks close to a normal. It's not a normal, but it's close. So now what we need to do is we need to do a little bit of algebra to make this look like a normal. One thing to remark is we have a k squared. Do we really want to have a k squared, or is there something else we might want to have? Well, we think the standard deviation is of size square root of 2n. So if we want to write this as a normal, it should be mean 0, and the variance should be 2n. And so we should have 2 times 2n, so we should have a 4n downstairs. We don't have a 4n downstairs. Yes?
But is that because there's a 2k?
Yeah, shouldn't this k squared be a 2k squared? Because we're evaluating what's the probability that x equals 2k, and we're expressing it in terms of k. We should express it in terms of 2k. Can I replace k with 2k? Only if I divide by 4. So this is the same as e to the negative 2k squared. Now I have a 4 down below, and I'm going to write the 4 as 2 times 2n. That's a great way to write 4. Over here now, I have a square root of pi n. So I'm going to write this as 2 pi times 2n, and square root of 2 times square root of 2 is 2, so I have to put a 2 upstairs. So algebraically, what I have done is legal. We replaced k with 2k because we're evaluating the probability at 2k. When we had the 4 down below, we wanted to write it as 2 times 2n because 2n is the variance, and the way you write the density of a normal is it's negative x minus mu squared over 2 sigma squared. So we wanted to write it as 2 times the variance. So over here, well, this is looking like the normalization constant of the normal. The variance is 2n, so let me write it as 2 pi times 2n. I've put a 4 down there. I've got an extra 2 over here. We are so close right now. With all the algebraic mistakes I've made, it looks like you've caught everything but one. We're off by a factor of 2 from being a normal. That's not bad, right? So we have 5 minutes to find the mistake, or to justify that there is no mistake. So, no, God, no. Error term has to be really small. If the error term is contributing, we're dead.
So you usually multiply by 2 when you get negative k squared over n.
No, we checked the algebra there. It is negative k squared over n.
Aren't we flipping 2n coins?
We're flipping 2n coins. Well, that's why we have 2n as the variance. It is related a little bit to the fact that we're flipping 2n coins. There is a natural reason for why we have this 2, and I gave a little bit of a hint about this earlier.
Symmetry.
Why symmetry? Somebody calculate very quickly. We're going to flip 4,096 coins, and I want the probability that we end up 2,015 steps from the origin. Okay, that was fast. Remember, we can't be an odd number of flips, or we can't be an odd number of net steps. If you look at the normal distribution is going to be nice and continuous. If you want to calculate the probability that you're at exactly 2k, we're not going to 2k minus a half to 2k plus a half. How far are we going? Not plus or minus a half, but plus or minus, I'm sorry? Yeah, we can do plus minus 1. And if we do plus or minus 1, the length of this interval is now 2. And if you want to approximate the normal density, you now want to integrate from 2k minus 1 to 2k plus 1, e to the negative t squared over 2 times 2n, 1 over square root of 2 pi times 2n dt. And if we now want to approximate this integral, when n is very large, does this integrand change that much as I go from 2k minus 1 to 2k plus 1? I can approximate this integral with just the midpoint of the integral, with the value of the integrand at the midpoint of the interval times the length of the interval. What's the length of the interval? 2. This integral becomes approximately 2 times e to the negative 2k squared over 2n divided by square root of 2 pi times 2n. So amazingly, you found every single error today. And here is a central limit theorem for tossing 2 unfair coins. There's a lot of algebra here, but there's a lot of good ideas on how to do the algebra and how to do the bookkeeping in such a way that at the end of the day you have an answer you can trust. We wanted to try to just use some crude approximations for E. If you're doing things only a fixed number of times, that's fine. But when the number of times you're doing it is growing with n, then you have the possibility of very small errors magnifying. And so we had to be a lot more careful. It's got to become instinctive. Whenever you see a product, you need to think logarithms. And logarithms are a great way to handle these products. You can then expand the logarithm with the Taylor series. And then we only really had to go down to depth 2. By the time you get to the third term in the Taylor series expansion, it's so small because of Chebyshev. One of the things I like about this is you get to see how some of these weaker results we did early in the semester can then kick in and help us get stronger results. We just need something on the order of Chebyshev to restrict the k. Once we have that, then we can do the more careful analysis and we'll get the central limit theorem. When we get to the proof in general, the proof in general is going to be very similar to this. The main difference is we're not going to be using Stirling's formula. We'll be using other things, but we'll be doing very similar approximations. We'll be doing things to the second order. This is one of the reasons why the central limit theorem exists. It's because these third order terms don't matter. And we'll talk about why this is so surprising. It doesn't really matter what shape distribution you start with. Things are converging to being normally distributed. Shouldn't the shape matter? If you're simulating from a uniform versus an exponential. It affects the rate of convergence. So I dropped all these error terms. Let's think about what would happen if we actually kept the error terms. So if we go back and we keep the error terms, we need to exponentiate this. If you exponentiate this, you get e to something of the order k cubed over n squared. Well, when n gets very, very large, what's the size of this exponential factor? 0. And e to the 0 is 1. And that's how you can make the analysis rigorous, is that these higher order terms aren't going to affect things in the limit. All right, so this is the central limit theorem in the case of flipping coins. Starting on Monday, we will do generating functions, and we will then start doing the preliminaries to prove it in